Thank you for having me here. Today I'm going to talk about my recent result with Robert Koenig on localization of any quantum circuit. So, let me just recall what was the fault-tolerant quantum computing in the sense of full operation. So let's say you want to, you're given some quantum circuit and you want to make it fault tolerant. Then it means like you're fixing some target accuracy here. I use epsilon, so that the output circuit Q prime should be epsilon close to your ideal quantum circuit Q. Here, closeness is defined as the total variation of the output distribution of two quantum circuits. And we all know that redundancy actually gives us fault tolerance. So in this talk, I'm going to say space overhead, which is defined as the number of qubits of the output state divided by the number of qubits of the input circuit. And also, I'll define depth overhead similarly. Here, I listed up some important results on fault-tolerant quantum computation. So here, Aharonov and Beno's paper actually proved constant threshold using concatenated codes, and their space and depth overhead were polylogarithmic. And later, Gottesman's paper, accompanied with a follow-up paper by Fauzi et al., and they constructed fault-tolerant quantum computation scheme using constant rate QLDPC code. And in their construction, space overhead was constant, but they had worse depth overhead, which scales polynomially. And finally, I want to mention the last scheme, Yamazaki and Kowashi's recent work. They constructed concatenated code with different lengths, and they were able to show that space overhead was constant and depth overhead was quasi-polylog, which is slightly worse than polylogarithmic scaling. Today, my main focus is geometrically local fault-tolerant quantum computation scheme, which is almost the same with non-necessarily local fault-tolerant quantum computation. But here, I assume that all the qubits are arranged in geometrically local lattice, meaning that every site has constant number of qubits, and all 2 qubit gates are applied to nearest neighboring qubits or constant radius neighboring qubits. So for example, when I say 2D local scheme, you can imagine kind of 2D planar, and qubits are arranged in this planar. And 3D local means you have kind of stacked planars. I try to categorize local fault-tolerant quantum computation and local quantum memories into 3 groups. So the first group is using non-local fault-tolerant quantum computation scheme and try to simulate it in local way by permuting your qubits using unitary swap gates. And because you have to permute your qubits extensively, it incurs polynomial depth overhead. But because of that, you don't really need much space overhead. And recently, there was a paper by Pattison, Krishna, and Preskill, and they constructed so-called hierarchical code, which was the concatenation of constant rate QLD PC code and surface code. Yeah. The second group that I classified was using local codes, which encode multiple qubits. So here, local codes mean that all stabilizer generators are actually local in the lattice. And there are some previous talks talking about the limitation of those local codes, so-called Bravy-Terahall bound or Bravy-Pauling-Terahall bound. So if your codes are local, then your code parameters should obey those constraints. So so the code parameters here I put here is actually optimal if you're considering local code in Euclidean dimension capital D. Actually, there were some recent progress on this approach to saturate these optimal bounds. Yeah. Here I listed up those works. So here, Portnoy's paper and a follow-up paper by Lin, Wills, and Choe, they constructed in the method so-called subdivided manifolds, and they could achieve the optimal code parameters up to polylog factor in the dimension of 3 or greater than 3. And there was a paper by Williamson, Baspin, and in their construction, they constructed so-called layer codes, and it was construction working in 3 dimension, and they could achieve the bound without a polylogarithmic factor. And last, and maybe the most important example is the lattice surgery with surface code. So here, non-locality is overcome by translation of your surface code tiles using lattice surgery technique. So let's say here you have some logical state Q at this tile, and you can actually translate your tile here to another position by spending not too much circuit depth. So our contribution is kind of combining first and the third approach. In our construction, we constructed so-called fault-tolerant routing scheme in quasi-2D and 3D lattice. Here, quasi-2D means that your lattice has height, which is scaling logarithmically in other dimensions. And you choose any non-local fault-tolerant quantum computation scheme. It can be your any favorite scheme, and you just combine them. And if you combine them, you naturally get a local fault-tolerant quantum computation scheme. What I mean by routing here is the following. So let's say you're given some quantum circuit Q prime. Here I made a diagram of some layer in this quantum circuit. And here you see gate 1 up to gate 8. And they are represented with red and blue color. And here I'm imagining like a circuit with 16 qubits. And I colored a pair of qubits in the same color if I want to apply some 2-qubit case on those qubits. If you're given some method for teleporting one of the qubit to another position like this, then you just solve the locality problem, because if you just teleport your qubit, and then they are so close, so you can just apply local operation on those pairs, and then you teleport them back so that you go back to the original position. And you can repeat this for given depth t prime times with different coloring, so that by combining this routing scheme with your given q prime, you can actually simulate q prime using local operations only. So let me state our result in informal version, which is slightly formal than the previous slide. So let's say you have this q prime local, which is noisy, where noise is of strength below some threshold. And then what we show this like is that there is another noisy version of your input circuit q prime, which is equivalent to the noisy version of q prime local. So here I represented error with this flash mark, and then you can prove that there is another noise of strength c times q to the c acting on your input circuit q prime, and they are equivalent. Actually, we also proved that they have constant depth overhead, and depending on the architecture, whether it is quasi-2D or 3D local, they have these space overhead. Right, and then let me describe how this is combined with the fault-tolerant quantum computation scheme, and recall the definition of fault-tolerant quantum computation, which was that for any noisy version of q prime is epsilon close to the input circuit. And therefore, if your equivalent noise c times q to the c is below the threshold of your input fault-tolerant quantum computation scheme, then actually the noisy version of q prime local, which is the final output circuit, is actually epsilon close to the input circuit. And you can get the total space overhead and depth overhead by just multiplying overheads of two different schemes. Here is just an example how it works, explaining how it works. So let's say you just chose your fault-tolerant quantum computation scheme as Yamazaki's and Kowashi's work. Their space overhead is constant and depth overhead is quasi-polylog. And given this overhead, we just multiply it by our routing space overhead and depth overhead to obtain those following total depth overhead and space overhead. Let me describe how routing actually works. So routing is nothing but parallel quantum teleportation or gate teleportation. And so it can be implemented by generation of long-range EPR pairs in parallel. Here, I'll describe one of the famous entanglement generation scheme, which is entanglement swapping. So here, you consider R sites where, and they are arranged in 1D chain. And each neighboring sites is sharing one EPR pair. And what you do is, for each intermediate site, you apply Bell measurement. And according to the measurement outcome, you compute the parity and apply correct Bell correction on each of on either site 1 or site R. This protocol can be considered as constant depth Clifford circuit with input state all physical zero state. And here, the important thing is this process is actually constant depth circuit. So keeping in mind this entanglement swapping protocol, we can actually route our qubits in parallel as follows. So let's say your input circuit qubits are arranged in this 2D ground floor, in this 3D lattice. And what you try to do is finding those collection of paths which are edge disjoint, pairwise edge disjoint. And according to that path, you can simply perform entanglement swapping under the assumption that your 3D lattice is full of auxiliary qubits. And there's a simple argument that you can always find those edge disjoint paths if your height is scaling linearly in the other length of the lattice. And there are some extensive research on like how to optimize the height of the lattice in lattice surgery related works, such as these references. But in this work, we just use very simple scheme to construct these parallel paths. And finally, I have to explain how to make your routing scheme fault tolerant. And here, so this is the first slide that I actually describe what is the noise model that I'm considering. So I'm considering circuit level noise, which is called local stochastic. So here, I'm considering between each layer of the circuit, there is certain random poly error. And the support of that poly error is containing some subset of qubits is bounded by p to the size of the subset of the qubits. And here, we don't exclude the chance that all these polys can be correlated. And the important ingredient for our fault-tolerant routing is so-called Rausendorf's cluster state, which is defined as follows. So you first prepare all plus state, and then you apply Control Z gate for each of the edges here. And you can think of this as kind of space-only version of repeated measurement of the surface code. Here I describe how to generate this cluster state and how to use that generated cluster state for generating belt pair from for 2 qubits here represented in green color. So basically, it's kind of similar decoding problem of repeat measurement of surface code. And here you can actually prove that this cluster state can be extensively large in terms of the code distance of the surface code. More concretely, we prove that the surface code distance can actually be logarithmic compared to the other dimension. And it still achieves some constant infidelity described like this. And the only remaining part for finishing the proof is to prove that this scheme actually works in parallel as well. And this is, in my opinion, not very trivial because we may consider some correlation between those different clusters. So so I thought this is not very trivial, but it actually works. So the noise strength of the output for this repeated parallel repeated version of entanglement generation has noise strength which is independent of the number of repetition you have. So because of this, you can route your qubit fault tolerantly in parallel. We actually proved this result with slight amount of generalization. So if you're interested in, then you can check our paper. And roughly speaking, if there is a family of errors causing your logical failure, and if it obeys a certain inequality, then your scheme actually works fault tolerantly, even with parallel repetition. Yeah. So everything combined together. Here, let's say your routing with non-fault tolerant version was this path. And what you simply do is replacing each of the segment of the path by this cluster state entanglement generation protocol. Okay. So here we conclude the talk. We propose a scheme for localizing any quantum circuit fault tolerantly. And we also prove a parallel repetition theorem. And I think this is kind of crucial ingredient for proving rigorous result on threshold theorem. And here, I wanted to mention that this construction is not strict 2D, which is considered, so maybe it's not super near term, but I'm also interested in modifying this result into 2D architecture. And I wanted to mention that the references 2 to 4 really motivated this research in the sense that they consider the trade-off relation between space overhead and depth overhead. So I'm still interested in checking whether this scheme is really optimal or not. I have some partial answer, but still it's not really clear. Okay, thank you.
Okay, we have time for questions. Any questions? Maybe what are these partial ideas that you have about optimality? Can you elaborate?
So in this paper by Delphos et al., they proved that if you want to apply some syndrome extraction circuit on constant rate LDPC code with expansion property, if you're assuming 3D and if your syndrome extraction has constant depth, then actually our non-fault tolerant version of routing gives you the optimal construction. But it doesn't really mean that there are some other possible fault-tolerant quantum computation scheme which is local, right? Because we are just considering LDPC code plus localization, right? So it's not fully proven that this is optimal.
Okay. Okay, any more questions? Oh yeah, in the back. Oh, sorry. Maybe this. Do you think your construction have anything to do with self-correcting memories in like 2 or 3 dimensions?
I don't think this is close to any self-correcting memory, but yeah, maybe we can discuss later. Because this is like, for routing, this is kind of active routing, so it's kind of far from self-correcting, I guess.
Thank you for the wonderful talk. I had 2 questions. Firstly, you mentioned that you can do this routing in constant time. So you mentioned there's this Delphos bound, which is between a trade-off between space and time, and your bound is more towards constant time, but has a high space overhead, right? So I was wondering, how can you route in constant time? Like, why are the circuits shallow? And the second question was, where did you use the fact that these are LDPC codes in the scheme? I mean, I know you input the Yamasaki and Kohashi scheme into your routing. But
you can use just LDPC code scheme instead of Yamazaki, but I'm just telling you that, for constructing syndrome extraction in local way, you can apply our routing scheme, and it gives you the constant time, constant depth, but large space overhead scheme. And if you know hierarchical code, and they sort of achieve 2D with large time overhead, but somehow constant or polylog space overhead. So
maybe one last question, if there's any. Okay, in the back. Hey, so if I understand correctly, your construction kind of does away with the fault tolerance requirements, and instead we just work at the bare level of the physical qubits to make these buses. And I'm kind of wondering, how does the volume of this bus compare to, say, like the space-time volume compares to, say, lattice surgery constructions or something like that?
I think volume for routing is kind of same. If you like, there are some room for space and depth overhead for lattice surgery, like how you pack your data qubits on this playground. And so if you pack your playground with many qubits, and it means like for doing long range, like for translation, you need to spend some time And it means that you have the same space-time volume, I think.
Okay. Yeah, so let's thank Shin-Ho again for the nice talk. And yeah, please let's reconvene outside where we can find the wine and cheese reception. Thank you.